learned that frequency stability is of the utmost importance. As an example, let's consider a radio broadcast station. One particular regulation prohibits the frequency of the station from changing more than a few cycles, so that the station will not interfere with another station operating on a nearby frequency. Now, for this reason, the oscillator producing this frequency must be one with the very best frequency stability. Oscillator capable of producing such an output is the crystal control oscillator. We're not going to study the oscillator circuit in this lesson, but we will study the characteristics of the crystals used in such a circuit. And here I might add that the crystal will be used as the frequency determining device of the oscillator. A crystal used in oscillator circuits must possess a characteristic known as piezoelectricity, or the piezoelectric effect. Now, the piezoelectric effect is defined as the property of a crystal by which mechanical stress produces electric charges, and conversely, electric charges produce mechanical stresses. Now, this is saying nothing more than if a voltage is applied to the crystal, it will vibrate. The amplitude of these vibrations are much greater at one frequency than at any other frequency. Now, this one particular frequency is called the natural resonant frequency of the crystal. Now, let's look at some of the crystal substances that possess the piezoelectric characteristics. They are Rochelle salt, tourmaline, and quartz. Now, of these three, Rochelle salts exhibits the piezoelectric effect to the greatest degree. However, quartz crystal is most generally used because it has a greater mechanical strength. Quartz crystal, remember, it has a greater mechanical strength. Now, I want to show you a piece of quartz crystal in its natural form. Now, if we were to examine this carefully, we can see that the quartz crystal has a hexagonal cross-section. That is to say, it has 6 sides. Now also, quartz crystal in its natural form has pointed ends. Now let's take a look at this drawing so that we can determine more about the quartz crystal. The top viewed indeed shows us that the quartz crystal has a hexagon shape, 6 sides. While the lower view points out that indeed the quartz crystal in its natural form does have pointed ends.
It'd be something like that, and it's got to be just right. And to see why you've got to get the angle just right, we need to look at the lattice structure of quartz. So quartz is made of silicon dioxide, so it's silicon and oxygen, and this is what it looks like. At first it looks like quite a complicated structure, but as you rotate the crystal, you find these symmetries like this one, and here's another. But there's one particular angle that I'm interested in, which is this one. Notice this hexagonal shape here. It's actually a spiral going into the screen, but for simplicity, we're going to think of it as a ring. So these 3 crunchy peanut butter lids represent silicon atoms, and these 3 smooth peanut butter lids represent oxygen. So when you compress a crystal of quartz, you're squishing these hexagons. But crucially, the bond between oxygen and silicon isn't quite even. Like, the oxygen is a bit more aggressive in the way it holds onto its electrons. So the oxygens are a little bit negatively charged and the silicons are a little bit positively charged. So think about where the average of all the positive charge is in this diagram. It's a bit like the center of mass, but it's the center of charge. So it's there in the middle between these 3 silicon atoms. But watch what happens when you compress the crystal. The two side silicons move outwards, but they don't move vertically. And the bottom silicon moves upwards. So the average position of these three positive charges moves upwards slightly. And similarly, think about the average position of the three negative charges. Look, the two side negative charges move outwards, but that top negative charge moves downwards, so the average of the three negative charges moves downwards. So when you compress a crystal of quartz in this exact orientation, you're slightly shifting all the negative charges in one direction and all the positive charges in the other direction.
Now, quartz crystal in its natural form cannot possibly be used in oscillator circuit. It must be cut in a specific manner to exhibit its piezoelectric properties. I know all of you at one time or another have heard of diamond cutting. The reason a diamond is cut is to give it brilliance, and the manner in which it's cut will determine its degree of brilliance. Now, all crystals are not cut in exactly the same manner, just as all diamonds are not cut exactly the same. The properties which a crystal exhibits are dependent on the manner in which it's cut. Now, there are many different cuts, but we're only going to examine three basic cuts. Let's go over and I want to show you the actual cuts now. I have here three crystal cuts. Now, all crystals look the same, but not all will exhibit the same characteristics. Its frequency will be dependent upon its thickness. Let's take a look at two pieces of crystal cuts and compare this difference in thickness. As you can see, the thinner cut here, the thicker cut here. We're indicating here that the vibration of this thinner cut, or the frequency, is greater than this cut. Now, this will always hold true. The thinner the crystal cut, the higher the frequency of oscillation. Now, there are a few other crystal cuts with better frequency stability, but these will not be discussed in this lesson. Now, when an extremely high degree of frequency stability must be maintained, the crystal will be placed in a temperature oven. A temperature oven is nothing more than a thermostatically controlled container used to maintain the crystal temperature in its proper range. And in doing so, of course, we have a high degree of frequency stability. Now, in order for a crystal to be used in an oscillator circuit, it first must be placed in a holder. Now, the crystal holder will support the crystal physically and provide the electrodes by which this voltage is applied to the electrode. The holder must allow the crystal maximum freedom of vibration at all times. Let's look at this drawing of a typical holder. The crystal will be placed in the holder between two parallel plates. The plates have an air gap between them, which allows room for the crystal to vibrate. Now, these are the pins that will allow the voltage to be applied to the plate. And also, the pins will allow the crystal to be connected into a circuit. Now, so far, we've seen the physical characteristics of the crystal. Let's now see how the crystal reacts electrically. To do this, we'll look at the electrical equivalent of a crystal and its holder. The crystal itself, when vibrating, acts very similar to a series resonant circuit containing resistance, inductance, and capacitance. Remember, this is when the crystal is vibrating. Now, when the crystal is placed in the holder, the capacitance of the holder will be placed in parallel like this. CH, the capacitance of the holder. So this capacitance represents the holder capacitance. This represents the vibrating crystal. Now, just because this vibrating crystal is equivalent to, or is the equivalent of a series LC tank circuit, I don't want you to think that it's the same thing, because the crystal will be far superior to the LC tank circuit. Now, the Q of the crystal circuit is many times greater than that of the LC circuit. Let's take a look at the comparison between the Q of a crystal and an ordinary LC tank circuit. The Q of an LC tank circuit is seldom greater than 2 south, whereas the Q of the crystal is sometimes as great as 30 south. And as comparing these two, you can see that the Q of the crystal would be many times greater than that of the LC tank circuit. Now, because of the high Q, this would mean that the crystal would have better frequency stability. Now, let's look at some of the values, both physical and electrical, of a typical crystal. If the crystal is going to be used in an oscillator circuit as the frequency determining device, let's take a look then at the schematic symbol for a crystal. These two plates represent the crystal holder, while this area would represent the crystal itself. Now, this is the schematic symbol of a crystal used in oscillator circuit. Now, let's recap a few of the points that we discussed in this lecture. First, we saw the use of the crystal. Now, we said that the crystal must exhibit the piezoelectric effect, and we defined the piezoelectric effect as the property of a crystal by which mechanical stress produces electric charges, and conversely by which electric charges produce mechanical stress. Then we saw the three substances used: Rochelle salt, tourmaline, and quartz. We said that Rochelle salt exhibits the piezoelectric effect to the greatest degree, but that quartz is most generally used because of its mechanical strength. This represented the crystal holder, this the crystal itself. Now, in concluding, we can say that the one big advantage of the crystal is its frequency stability. Remember, it has a very high Q, giving us a very narrow bandwidth. That just about concludes the lesson on the characteristics of crystals. So until another time, so long.